The topic of this video will be alkoxymercuration-demercuration of alkenes. This reaction is very similar to oxymercuration-demercuration of an alkene, except that our nucleophile is an alcohol instead of water. If we treat this alkene with a mercury catalyst and an alcohol, we get the mercury-containing intermediate that is an ether instead of an alcohol. Reduction of this intermediate gives us the ether product. Just like oxymercuration-demercuration, this reaction is regiospecific. We see only the Markovnikov product, with the ether being added to the carbon that is most substituted. This reaction is also stereospecific. We see only anti-addition of the ether and the proton. Now we will look at a specific example of this reaction. If we treat this alkene with a mercury catalyst and methanol, followed by sodium borohydride, we get a single product. We do not get the anti-Markovnikov product, or the product that would be the result of a carbocation rearrangement, because no carbocation is formed in this mechanism. The first step of this mechanism is similar to oxymercuration-demercuration, in which the mercury catalyst ionizes to form the active form of the catalyst. In this step, the acetate group leaves, producing the mercury cation and free acetate. Remember that mercury in both of these cases has a lone pair of electrons. Next, the alkene attacks the mercury carbocation, and the mercury lone pair attacks the alkene back. This forms the cyclic mercury intermediate. Another way to think about this mercuric cyclic intermediate is that it has several resonance structures. In this resonance contributor, the positive charge is on the mercury. However, we can draw resonance contributors where the positive charge is on the carbons of the mercuric intermediate. For example, here is one resonance contributor that has the positive charge on the secondary carbon of the cyclic intermediate. Another possible resonance contributor can have the positive charge on the other carbon. All three of these are resonance contributors to the same overall structure. The major contributor is the structure that has complete octets around all of the organic molecules, atoms, which is the top structure. The most minor structure is the structure on the bottom right that has an incomplete octet on a carbon that is only primary. The resonance contributor that has a secondary carbocation is the second most major contributor to the resonance hybrid, meaning that it contributes to the overall resonance hybrid more than the other carbocation. This is why we say that the secondary carbon of the cyclic intermediate has the most partial positive character as compared to the primary carbon. Therefore, our nucleophile will attack the carbon with a greater partial positive. It will attack this carbon, opening up the mercury intermediate. Next, another molecule of methanol will deprotonate the ether. In the final step, sodium borohydride reduces away the mercury and replaces it with hydrogen. This gives us the ether product and the Markovnikov product with respect to the regiochemistry. Next, let's look at the stereospecificity of this reaction mechanism. If we treat this alkene with a mercury catalyst and methanol, followed by reduction with sodium borohydride, we get two products. We see anti-addition of the alcohol and the proton. So we see this molecule and its enantiomer. We see only these two stereoisomers of 4 possible stereoisomeric products, and this is due to the mechanism and the fact that the alcohol and the proton are added anti. Take a moment and pause the video and see if you can draw the mechanism for this reaction and predict why we get only these two enantiomers as products. Addition of the active mercury cation catalyst to the alkene occurs with attack of the alkene on the mercury, followed by the mercury attacking right back to give us the cyclic intermediate. This can occur from the top face or the bottom face of the alkene. Next, attack of the nucleophile occurs. Attack of the nucleophile must occur anti to the mercury in order for orbital overlap to occur. This is similar to why E2 requires the proton and the leaving group to be anti to one another. Therefore, if the methanol attacks the top carbon of the top structure, it must come from the top, the front of this structure, and therefore produces this product. If attack of methanol happens on the top carbon of the bottom structure, this attack must occur from behind the carbon, from inside the page, and therefore produces this product. The next step is deprotonation of the ether. Another molecule of methanol deprotonates the ether to produce the neutral ether intermediate. Reduction with sodium borohydride of the top structure produces the bottom product, and reduction of the bottom structure gives us the top product. It is in this way that we get only these two enantiomers as the products of this reaction.